Hello and welcome, everybody. Today in calculus, we will be looking at a new chapter, a new, item for your second semester of calculus. So this is probably one of the last few chapters of the semester because after this, you're pretty much going to go into new territory, and that's where your college professor is going to come in. So let's just see how this one works out. Okay. So this section or this entire chapter is on something called differential equation. So modeling differential equations. So this first section is going to be kind of like an introduction in a way. Okay. So back in chapter 3, a long time ago, we defined the following: a differential equation. A differential equation is defined as any equation that contains its original equation and some form of its derivative. So, for example, underneath right here, there are some following of examples of differential equations. So in the first one, you can see here you have y prime is equal to 3y plus 2. So that's a differential equation because you have the derivative in there and also you have y, the original equation, in there. The second one right here, that's also a differential equation because, again, you have some form of its derivative and the original function itself, p double prime, p prime, and also p. And then the last one right here, that's also a differential equation, but just written in a different form. So it's dp dt is equal to k times p, where k is going to be some sort of constant. Now, the first two form right here, it's a little bit deceiving because you don't know, or you're not really told what the independent variable is, because it could be x, it could be time, or it could be t, whatever it is. A majority of the times with differential equation, the independent variable is going to be t unless they tell you. So it's in a way better to write it in the third form if you can. Rather than writing y prime, it's probably best to actually write it as like dp dt if possible. Okay, so that is going to be our second part. Now, the thing about these differential equations is, well, for one thing, like I said, time is usually the independent variable, and these are some examples of it. Most differential equations can't be solved. They just need to be translated. So a while back, about 10 years ago, when I took this course with a college professor, just to kind of, as a refresher, the best example that he gave me, or best analogy that he gave me, is the following. Let's say that you have a board over here, and that represents all the differential equations that you can set up in the world. In terms of how many of them you can solve for by the end of your math career, most likely it's going to be about this much right here. So it's going to be that little small dot amount. Okay. And it's not to be, it's not to make you feel bad or anything about it, but that's just the reality of things. A lot of times you're not asked to solve for these differential equation, but more importantly, you're asked to maybe decipher it, so then that way you can translate to other people as to what they're meaning and how is it useful and that kind of stuff. So it's if you can solve more than that, then sure, it's kind of great. But for the most part, it's just a lot of flexing mathematically, and that's what we call masturbation. So it's basically not really necessary. So anyhow. Now we're going to go ahead and look into some sample equations or sample stuff that you can do, or that that deals with this differential equation thing. So here is a problem that gives you an idea as to where differential equation comes from. Now, here it says that the rate of growth of a population is proportional to the population size. So meaning that your growth is always determined by how big your population is going to be. Suppose that the initial population is supposed to be 500. Solve for the equation P of t, which solves for the population at any time or any year t. So let's go ahead and set up some sort of differential equations for this. In your first part of the statement, in your first sentence, you can see that the rate of growth of population, so that means that we're referring to dp dt, okay, is equal to proportional to the population. So that means it's going to be some constant multiplied by the population, so k times p. And hence, earlier, that's why I gave you this example of a differential equation. So what I'd like to do is, given this differential equation, I want to be able to kind of work backward if possible to figure out what is this population equation then. We are also told that the initial population is going to be 500. So that means when p when t is equal to 0, that means that we are going to have p is equal to 500. So usually that's how it's denoted. All right, so let's go ahead and see if we can work backwards from this case. Let's see. Now, what I think is best in this scenario is that we're going to go ahead and separate your variables. So that means that I'm going to go ahead and put p on one side, and I'm going to go ahead and put t on the other side. K, I'm just going to go ahead and keep it as the same because it is a constant, so we don't have to worry about that. And once we isolate the variables, then we can go ahead and integrate both sides. So this technique is what is known as separation variable or separate variables. And it's one of the few ways to solve for differential equations. Okay, so separate variables. Okay, so we'll go into a section a little bit later on that talks about this a little bit more, but this is just to give you kind of an intro. So taking the antiderivative of both sides, we're going to have ln of absolute value of p on the left is equal to k multiplied by t and then plus c, because the variable over here is time. So k, if I take the antiderivative, is just t in this case, k times t. And then we also add a constant. In terms of where do we add the constant, does it have to be on the left? Does it have to be on the right? I usually just put it with the independent variable. You could put it on either case. Do not put it in both because that would actually kind of, confuse things if anything, right? So if you were to put like say ln absolute value of p plus c is equal to k times t plus c because you're saying, oh, I integrated both sides, so therefore there should be a c in both sides. That is just kind of weird because for one thing, you don't know if this c is going to be the same as this c. So in a sense, what I'm saying is because c is a constant, you can just add it or subtract it to either place, and it's probably best to just add it to one versus to add it to both. So we're just going to go ahead and add c to one side, and preferably it's going to be the independent variable side. Okay, we can go ahead and keep solving for p right here because that's what I need, right? I need to solve for that equation. So let's go ahead and take e to both sides then. So we have p absolute value is equal to e raised to the power of k times t and then plus c. And according to what we have right here, since p represents population, and if you notice the right-hand side is an exponential function, then that tells me I can actually drop the absolute value sign. So that is to say now p is equal to e to the k times t plus c. Or if you want, we can say p of t just so you can say that it's a population in terms of time. Now, there's still the matter of solving for the constant. So then that means that we need to actually put that somewhere, or we need to figure out how that actually works out. It's kind of like saying, you take the antiderivative, I need a specific equation, so I need to solve for what c is equal to. So in order to do that, what we'll do is we're going to go ahead and rewrite that equation on the right-hand side. I'm going to write it as e to the k times t and then multiply by e to the c. Okay, basically using the property of exponents. And e to the c, well, that's still a constant because if c is a constant, then e to the c is also a constant. So let me go ahead and call that constant c1 or c naught, whatever you want to call it, just to make it a little bit easier. So then that means now our equation is going to be c1 multiplied by e to the kt. And at this point, we can go ahead and plug in the initial point then. So let's see, p of 0 is equal to 500 is equal to c1 multiplied by e to the k times 0. This guy right here, e to the k times 0, that's equal to 1. So that means that c1, this variable over here, is going to be equal to 500. And it's always going to work out the case where that is going to be the initial population. So finally, my equation is p of t is equal to 500 multiplied by e to the kt. And hopefully this looks somewhat familiar because back in algebra, you were always told that whenever you have a population equation, it's going to be exponential. Well, here's the derivation as to why. And in addition to that, you can see that the initial population is always in the front as a multiplier. All right, so that's going to be the idea behind this differential equation, and we'll definitely look at more in the future. Now, let's look at some other problems over here. So in this case, again, this section is on just taking the intro of this. What I want to do is I want to verify or show that the following are solutions to the differential equation y prime plus x 1 over x times y is equal to 1. So what I did was I wrote down three problems right here, three different equations or three different technically quote-unquote solutions, and I want to verify that they work. So the best thing that we can do is literally plug each one in there and see what happens then. So here in the first case, we have y sub 1 is equal to x over 2. Now, if I were to plug it into differential equation, I need to solve for y prime first. So that is going to be equal to 1/2 because I'm just taking the derivative of this guy. Now we have everything to go ahead and plug into our differential equation. So let's see, y prime, which is going to be 1/2 plus 1 over x multiplied by y sub 1, the original equation, is going to be x over 2. And does that equal to 1? And if we clean up the math over here, you can definitely see that should work out because the x's cancels out. And all I'm left with is 1/2 plus 1/2, which does equal to 1. So that checks out then. Let's try the second one. Do this exactly the same thing. This time we have another equation. We say y sub 2 is equal to c divided by x. So just like before, I'm going to go ahead and solve for the derivative of this equation. So that's negative c divided by x squared. And I'm going to go ahead and take these two and plug them into the differential equation. So same as before. So y prime, so that is going to be negative c divided by x squared. And then plus 1 over x multiplied by c divided by x. And the question is, does that equal to 1? If we clean up the math here, we get negative c over x squared and then plus c over x squared. And in this case, you'll see that unfortunately it does not equal to 1. So then that means that this is not going to be a solution then. So not a solution. Okay. And finally, for y sub 3, you get to do exactly the same thing, but you get the idea as to what's happening over here then. Okay. So let's just finish it off. So y prime of 3 is equal to c divided by x squared, and then that's going to be negative. And then we also have plus 1 over 2. So I'm going to take these two guys and plug it into the differential equation given to us. So let's see here. That's negative c over x squared and then plus 1/2. And then plus 1 over x multiplied by my original equation. So c over x plus x over 2. And does that equal to 1? So cleaning up the math a little bit, we have negative c over x squared. And then we have plus 1/2. And then plus c over x squared. And then we also have plus 1/2 in this case. So let's see, the c over x squared, that's going to cancel out. So then 1/2 plus 1/2 is equal to 1. So yeah, that's going to be a solution then, right? So there you go. That's how you can verify that if you have a differential equation, the solution that's given to you could be a differential equation or not. Okay. All right. Finally, or a few more things, is that the order of the differential equation is equal to the highest order of its derivative. It's just basically like a polynomial. So for example, if you have y triple prime minus y is equal to sine of t, we call that a third degree differential equation because at the very beginning, you have y triple prime, and that's the highest derivative order in this case, okay? All right, so let's see here. Let's see. Like I said earlier, what I need to do, and this is probably the last part. I thought it wasn't at first. The last part over here is, remember earlier we were saying that, when it comes to differential equation, we don't really care too much about solving for them if possible. Instead, it's nice to be able to solve for it, but you don't really have to do it all the time. Instead, it's probably better if we can kind of just translate it. And that's what this problem over here is going to be for then. So this time I'm going to say let dp dt is equal to p squared plus minus 5p plus 4. So this could represent, like, say, a population growth and how it's supposed to be dependent on the current population. Now, what I want to do is I want to solve for the following. I want to know for what value of p, or for what value of the population, is the population increasing. So that is to say, I want to know where dp dt is going to be increasing. Well, this right here, let me just go ahead and translate that according to how we've been doing it so far. According to my first semester of calculus, this means that dp dt has to be greater than 0. Now, one thing you can thinking of is that, oh, okay, well, earlier I was able to solve for the equation of p of t, right? And then afterwards, well, why don't we go ahead and take its derivative and then set it so that find out where is it greater than 0. That's going to be kind of a roundabout way of doing it, and we don't really need to do that, okay? Instead, why don't we just take it for its face value, right? I'm really just looking for where dp dt is greater than 0 for p. My entire equation is in terms of p, so then that means just by substitution, then I'm looking for the following. P squared minus 5p plus 4 is greater than 0. Well, that's easy enough to solve for because we really just have something that's quadratic. So let's see here. That's p minus 4 multiplied by p minus 1, and that's going to be greater than 0. And if we were to kind of like sketch this out, right, as a curve as to see how this looks like, let's say that my independent is p, and then my dependent is going to be p prime, right? Be very careful. We're not graphing the actual equation, but rather just the relationship between p and p prime. This guy right here is a parabola. It's a parabola that's opening upwards, where 1 is over here, 4 is over here, and those are going to be my zeros. So then that means that the parabola looks something like this. And now you can clearly see where p prime is going to be greater than 0, where p prime is going to be greater than 0. My solutions are going to be, according to this, when p is going to be between 0 and 1, inclusive of 0, exclusive of 1, because 1 you get 0. And if you're wondering how come I don't include p that's less than 0, well, that's because population is positive, right? It's never a negative number. Or the other case is when p is greater than 4. So that's when your population is going to be increasing then, okay? Now, for the second one, it's kind of the same deal. We can actually work off of the previous one. For what values of p is the population decreasing? Well, that means if I'm translating it just like before, I'm looking for where dp dt is going to be less than 0. Well, you can see it again from the graph that I have right here. So that is going to be between 1 and 4, and we're going to go ahead and exclude those endpoints. Okay, so notice again, we don't actually have to solve for the differential equation. We can just translate it as best to our knowledge. And then finally, for this last one, for what value of p is the population at its equilibrium, so no growth or no decay. So meaning that my rate of growth is not going to be anything. It's not increasing or not decreasing. So that means that we're looking for dp dt is equal to 0. Well, judging from what's here, we're looking at when the population is equal to 1 or when the population is equal to 4. Okay, so those are going to be my answers. And for this last one right here, at what value of p is the rate of the population at its maximum? And I think I need to change this problem because according to what we have right here, we really shouldn't be looking for maximum, but rather a minimum in this case, okay? So again, looking at my graph right here, you can see that it's supposed to be at its vertex. So that means it's supposed to be over here, most likely the average between 1 and 4, which is going to be equal to 2.5. So that is going to be my answer in this case, when p is equal to 2.5. Okay, let me go ahead and change it. So p is equal to 2.5. But yeah, you know, that's pretty much it. Okay, so nothing really difficult, hopefully. All right, well, we'll go ahead and talk about a little bit more of the differential equation next time. I will see you later and have a good one. Goodbye.